Hi class, in this video lesson we're going to be reviewing, to start, some of the key terms related to solutions. So I've just prepared this concept map just to review these key terms. So we have solutions at the top. They are a one-phase mixture. We call that a homogeneous mixture. The main component in a solution is the solvent, so they consist mostly of solvent. There will be some dissolved solute. There are different types of solute-solvent combinations I haven't included here. Gases can dissolve in gases, gases can dissolve in liquids. Commonly, solids dissolving in liquids is what we usually think of as a solution. And in that case, when water is commonly used as the solvent, we would call that an aqueous solution. If the solution conducts electricity, we call that an electrolyte. And if it does not, it's a non-electrolyte. And non-electrolytes are usually molecular solids. They'd be neutral molecules. Could be elements, could be compounds, but covalent bonding involved in those. Electrolytes are usually ionic solids, as well as we have acids and bases, both of which could be ionic, although more commonly we have ionic bases and molecular acids, but there will be some of each. Ionic and molecular acids and bases. And we know for acids and bases, both will affect red or blue litmus paper. So we can kind of look at this as an overview of solutions, and we can use the properties of solutions here to identify unknown substances. We can also use that concept map to fill in some diagnostic tests that could be done to identify the type of solute. So if in this worksheet, you were to go through these, and for the first four, you should be able to use the concept map directly to identify the diagnostic tests that would involve litmus paper or conductivity. And just to remind you that in the case of conductivity, we can use a conductivity meter, which just measures electrical current in a solution. Number 5 is identifying the solute and solvent. So when we see AQ, that's aqueous water, would be the solvent. The solute, of course, would be the solid form of the compound. In the case of Al, that would be alcohol. And sometimes solutes can be more soluble in alcohol than water. Bromine in that case is solute, is dissolved to make a solution in alcohol. Number 6 is a bit of review as well, but also looking here at writing experimental designs, so identifying the variables dependent and independent, as well as any controls that would be used here. We can discuss this in class based on your answers. You don't need to go as far as writing a procedure, but you should at least list the materials that would be involved in that. When we look at the handout that summarizes 6.2, it's a fill in the blank note, and I'm going to go through the bulleted points here, all the way down to the bottom where we'll visually represent the dissolving of molecular and ionic solids. So let's have a look. In this practice questions worksheet here, we have the solutions as well for 6.1b. When you go through your answers, I'll reveal this at the very end if you want to check any, if you've already started working on it. Maybe you've paused the video. The worksheet here, the note rather, for explaining solutions. First point is that when something dissolves, it's a result of intermolecular forces, an attraction between solute particles and solvent molecules. There has to be a breaking up of the solute particles, or at least a division or separation of them, depending on what form they're in. And the solvent molecules do that breaking up or separating. So the intermolecular forces are really important here, and the stronger they are, the more easily the solute will dissolve. When we look at the most common solvent, which is water, what makes it very effective as a universal solvent is that the water molecule has polar bonds, and that allows water to attract either polar molecules themselves, which also have that dipole, or it allows them to be slightly attracted to charged particles, positive and negative. So depending on the solute, we find that polar and ionic solutes, the first key terms there, dissolve well in polar solvents. Water is the chief example there. And that nonpolar solutes dissolve well in nonpolar solvents. So if our solvent contains weakly dipoled atoms, or in the case of maybe a solvent that was a pure substance as an element, which would be entirely nonpolar, a nonpolar solute would dissolve best in that. So classic example would be oil and gasoline, or quite commonly hydrocarbons in other hydrocarbons. So hence the expression we say like dissolves like. Now, when we talk about the breaking up of ionic compounds, we refer to this as dissociation. And dissociation is a separation of the ions in that network of the crystal lattice. They're breaking up. As they separate, there needs to be a force that encourages them, we'll say, to separate. That happens as they're attracted by the positive and negative dipoles in the water molecules. If we were to look at some visual examples of dissolving, we could see here intermolecular forces and dissolving, illustrating dimethyl ether dissolving in water. You can see that the water molecules surround the solute molecules, which in this case are not charged ions, but they do have a dipole. We would have some positive character to the hydrogen atoms and a negative dipole on the oxygen in the center of the molecule. And so visually here we can also see that this rectangle of red and green ovals would represent the solute molecules in red being surrounded by polar solvent molecules. And once the solute molecules are completely surrounded, we would say that the substance has been dissolved. There's no evidence of its original form. When we have multiple hydrogen bonds between the solute and the solvent, that allows for very high solubility. In the case of the dimethyl ether, it's not much of a dipole within the CH3 group because carbon and hydrogen, their bonds are weakly polar based on the electronegativities of hydrogen and carbon atoms. So we don't have to have dipoles throughout the molecule for something to dissolve, but the more dipoles we have, the easier it is for the solvent and solute particles to interact. So that's visually how dissolving works. As we return to our note here, some dissociation equations that we can write. Sodium chloride breaking up into sodium and chloride ions. They're aqueous. In that case, we assume water is the solvent. Magnesium phosphate dissociating into 3 magnesium ions and 2 phosphate. What you really want to take note of here is that as the ionic solid breaks up, the number of ions that are produced is simply just the number that are contained in the crystal lattice. So we know magnesium phosphate has 3 magnesium ions for every 2 phosphate in the formula unit. So when that formula unit dissociates, that's how many ions we will obtain. When we look at these dissociation equations here, the key thing to remember though, this is a physical process, so it's not a chemical reaction exactly. These ions, the magnesium and the phosphate, are just as much present in the ionic solid here. The formula unit doesn't show the charges on them, of course, but we do remember that the crossover rule of the charges is what we use to obtain the number of ions of each type. And so remember that 2 and 3 do come from the ion charges. So these are physical processes, and in these two equations, they do clearly illustrate that mass is conserved. We have the same number of ions of magnesium, phosphate, sodium, and chloride on both sides. So mass is conserved, as well as you'll notice charge is conserved. The left side shows no overall charge. We understand it to be a balance of positive and negative ions in that formula unit. And on the right side, we see the charges, but we also can clearly identify that we have as much positive and negative charge. We have +1 balanced by -1. Here we have 3 times 2 or +6 balanced by a 2 times -3 or -6. So mass and charge are the two properties being conserved. Okay, now for the remainder of this note here, let's just reveal the last part. You're going to show the dissolving of molecular and ionic solids visually. So what I would like you to do now is to draw the following. A molecular solid is one which is made up of a molecule, so it's a covalently connected particle. So the bonds between the atoms are covalent bonds. All nonmetals, and in this case sugar is a good example to use because carbon, hydrogen, and oxygen are all nonmetals. When sugar dissolves, we get aqueous solution, of course, because water is the solvent, but we don't get ions. So the dissolution process or dissolving process has the water molecule surrounding this small little molecule of sugar, which makes it invisible to the eye when it's broken up and it's now in the solvent. Same can happen in this case with sodium chloride, where the sodium and chloride ions are broken up and the ions are surrounded by the different ends of the water molecule. Depending on the charge of the ion, the water molecule will orient itself differently, but it'll still be able to attract it. So in the case of the sugar dissolving, of course, we don't get ions in solution, so it's a non-electrolyte. Sodium chloride clearly is an electrolyte when it's dissolved. And the type of particle in solution will differ. So we can use conductivity as a way of determining whether the solute was molecular or ionic. We go back here. This pretty much wraps up our note. We have key properties reviewed, and at this point now you should be able to go through and complete the original worksheet as mentioned, as well as the assigned questions at the bottom here, which we can work on in class. Take care.